All right, so what we're talking about is the story from 1967, which is the year I got my PhD, till 2010, which is when I retired, and I really stopped doing physics in 2010. And I'll talk about that a little bit later, but there are roughly 3 stages in the development of a theory. You can say there's prehistory. So in the prehistory, we know lots of pieces, but we haven't put them together. And so the theory really doesn't exist, even though many of the pieces that will become the theory are beginning to be understood. Then there's the emergence, when things start to come together and we begin to really understand how that theory works. And finally, there's consolidation, when we really have written the theory down in a well-defined way, and now we're testing and making sure, and we're seeing all the places we can apply it and testing in new places. And the theory goes through that phase for the rest of its life, unless something really amazing happens. And what we hope in the consolidation phase, we get to the point where it's so well tested that we want to break it. Because the only way we make progress is by not having a theory we understand and having data that doesn't fit the understood theory, that we have to do something new. This theory is so good that it emerged, I would say, in around about, well, I give it a single year, 1974. And since 1974, it's been tested in very many ways, and it's still working. We don't have good indications of what next we need to do. We know it's not a theory that doesn't, we know it's a theory that doesn't explain everything about the world that we would like particle physics to explain, but it's a very complete framework, and it explains an incredible amount of data. And I was happy my career matched this time. I had the good fortune during my career to be in places where this theory was evolving. So I did my PhD at SLAC from 1963 to 67. And my thesis advisor was BJ, namely James Bjorkane, who developed one of the major pieces of theory that allowed us to understand the data that told us that quarks exist. Talk a little about that. And I was working with him on things related to that as a PhD student, because I didn't really understand all their implications, but it was a good place to be at that time. Then I had a few years where my career was going nowhere, but I finished up in the Cambridge area and went to Harvard. I'll tell you more about that. And that was a period where Harvard was the place where this theory was emerging, and many of the people who were doing fundamental things were there. And so I was in a place where these ideas were just bubbling, and it was really fun to do physics there. And then when I left Harvard, I went back to SLAC, or back to Stanford and SLAC, and again had good colleagues working in the same kinds of areas and could be part of what was going on in that era. So being in the right place at the right time is really valuable for advancing your career in physics, and I was fortunate to do that. And the other thing is, when the theory is new, nobody's an expert because nobody has worked with it for very long. And so a graduate student or a student working, somebody young working in the field knows as much about that part of the field as anybody does. And therefore, it's easier to make forefront contributions early in your career if you're in that environment. So I was very, very fortunate in all of that. So what is the standard model? Well, we have to say, what are the particles we're talking about and what interactions we're talking about? By the 60s, we had a lot of particles and not much theory. Theory, when I was a graduate student, we had names for lots of particles. We had essentially no theory for the strong interactions. So let me just talk about the names, because I'm going to be using them, and if you don't know them for an undergraduate, I need to define them. Hadrons means any particle with strong interactions. The ones that don't have strong interactions are called leptons, because the early ones were all very light particles. And lepton means light particle, apparently. But some of them are heavier now. Then the other part is, we knew about antiparticles. That in itself is an amazing piece of history in physics. I think Dirac's equation, when Dirac first wrote down an equation that could describe the physics of particles with spin a half, the equation told him there had to be antiparticles. He fought it for a little while. He didn't make that interpretation immediately, but eventually realized the equation was saying for every particle you find with spin a half, there's going to be an antiparticle. And it wasn't that long until the positron, the antiparticle of the electron, had described. But it's actually really amazing that mathematics could tell us something that no physicist would have thought of without the mathematics saying us. And I think particle physicists take that example to the extreme as they formulate new theories, trying to go beyond the standard model with no particular evidence. They know that their theories can add particles, they can add interactions, they can add things that haven't been seen. And maybe the mathematics will then tell the experimentalist where to look. All right, so all of that is in place, lots of it. The interactions we're talking about, well, gravity is not included. I'm not going to mention gravity today, but the electromagnetic interactions, there we had a field theory. There we knew how to do some calculations, but it was really the only one. The weak interactions, we had a theory which fit the data if you calculated the leading term, but if you tried to do the next order in perturbation theory, you got infinity. You couldn't get rid of it. Or to fix the infinities, you had to add an infinite number of additional terms to the theory. That's called non-renormalizable. Those kinds of theories don't make any predictions because you have to have too many parameters. So that was not very good. So we knew the weak interaction theory was pretty sick. The strong interactions were even worse. There was essentially no fundamental theory of strong interactions. There were nuclear physicists who tried to explain the interaction between protons and neutrons in nuclei by developing an effective potential. And that had very little to do with all the particles were discovered trying to refine that theory. And instead, you found something that didn't fit that theory very much at all. So we'd sort of gone beyond any level of understanding strong interactions by what we discovered by trying to understand strong interactions. And we just had a mess. That's the picture in 1963, 64, where I was taking courses about what is particle physics. This is my passport photo from 1962 when I came to the US. So I was in grad school. I've already said I arrived at Stanford in January 62. I was 1 year there as an undergraduate, and then I stayed as a graduate student. And as Max said, women in the field were very few. But you notice that the curve of women in physics is much smoother than the curve of men. The curve of men is relating to funding for graduate students in physics and things like that. The curve of women is going sort of steadily up, but slowly. And there's still only, this curve ends a few years back, but I think it hasn't changed much. 16, 17% of PhDs in physics go to women. When I graduated, it was 2. So I've already said this. What I learned was incomplete, like QED. QED is a very good theory, and perturbation theory works unless you get to very strong electric and magnetic fields, and then it's a mess. Then there were other theories which still correct, but they weren't answering the questions we wanted. They're only partial theories. And then there are theories that weren't even defined enough to call them wrong. They just were wild ideas, if you like. And mostly what we could do was make tables of what particles had been found and put them into groups with similar properties and similar spin and mass. And doing that had led to a theory that in 1964, Gell-Mann said, well, I can explain this mess of hundreds of particles if there are 3 types of quarks, and they're all made of quarks. And that's a good mathematical explanation. And Gell-Mann actually talked about mathematical quarks. Nobody really took quarks seriously as physical particles because they had charges that were a fraction the charge of an electron or a proton. And nobody ever saw such charges. People did a lot of hard work searching for fractional charges and never really found them, although sometimes some people claimed they had. It never survived serious attention. So quarks didn't seem to exist, and yet they seemed to explain all these massive particles. That was very confusing. And so physicists went to something called current algebra. Current algebra was a way of calculating some of the consequences of quarks without talking about the quarks. What you did is you derived currents from the quarks. You said, I can derive these commutation relations between currents, which are the currents of the strong interactions of hadrons, if I assume quarks are free particles at high energy. Now, we knew no theory where the particles got free at high energy, so that was crazy. And we'd put that all together, and we could derive results from that current algebra. Well, the quarks in the current algebra turned out to have masses. So there are, in Gell-Mann's quarks, there are 3 in a proton. But the current algebra, you could calculate the masses of the quarks, and they were much less than 1/3 of the proton mass. And that didn't make sense. So even when he was doing current algebra, Gell-Mann wrote papers in 1966. He proposed the quarks in 64. In 66, he wrote a paper talking about mathematical quarks and real quarks. And real quarks were ones that didn't explain the particles, and mathematical ones were ones that did. So clearly, everybody was confused. In 1964, he proposed them. I've already said all this, so I'm going to skip forward. Current algebra, I've said all this. So now we get to emergence. 1967, Steve Weinberg writes a paper. He calls it a theory of leptons. He didn't talk about hadrons because if you took this theory and generalized it to quarks, it didn't work. But it is the standard model. It is the beginning of the standard model. He wrote down the standard model, but he wrote it just for leptons. In 1967, that paper is the foundation of his Nobel Prize, but it got essentially no references until 1971. And the reason is, not only did it not work when you tried to make it the quarks, but it also didn't look any better than the other theory we had for weak interactions. It was a theory of the weak interactions of electrons and muons and their neutrinos. And nobody could calculate the next order correction. So for technical reasons, we didn't have a way of making the integrals temporarily finite so we could see if they canceled one another. We didn't have a way of what's called regulating the theory. And it wasn't until 1971 when 't Hooft and Veltzman gave us a way of regulating the theory, making the calculations reasonable to do, that you could even see if this theory was any better than the theory it was trying to replace. So, why no hadrons? I already told you that. But he went ahead and published it anyway, even though he knew it didn't work for the quarks. That's a good strategy. When you have a theory that looks as if it does something good, and there's a part that doesn't quite work yet, you can either spend a lot of time trying to figure out how to make that part work, or you can publish the part that works and say, at the end of there's some questions here. And one of the questions is, how do we generalize this to the hadrons at the end of your paper? And that's what he did. And that was a good thing to do because we all needed to read his paper. Okay, one of the things in his paper that I'm talking about, and I'm going to talk about it several times, so I will, and the ones who came to lunch saw this example already. Spontaneous symmetry breaking is a key to this theory. What is spontaneous symmetry breaking? Well, you see here. First of all, you have to understand that when physicists say symmetry, what they actually mean is a mathematical invariance in the equations. So that means if let's take the pencil standing, the pen in this case, standing up on the table. There's a symmetry about the axis that's, if you make the vertical axis go right through the pen, it doesn't matter which direction in the table I pick the x-axis for, as the equations are going to look exactly the same. That's an invariance. That's a mathematical invariance in the equations. So symmetry, of course, means something to us visually, but what physicists mean by any such invariance, where the equations don't change when you change something about the variables you're writing them with. So in this case, it's, when I talk about symmetries, I don't necessarily mean spatial symmetries. But anyway, symmetries can be symmetries of the equation. In this case, the equations that describe that pencil and all the forces on it, totally symmetric about the pencil. However, that's an excited state. It has higher energy than the ground state, which is when the pen has fallen over. And when the pen falls over, it can't fall over without breaking the symmetry. It's got to fall in some direction. So the equations don't tell it which direction to fall. That's somehow random. I mean, in the real world, it's probably because the wind blew or something like that. But in quantum mechanics, it's just quantum fluctuations that make the particle go from the excited state to the ground state. And the symmetry is broken. So that's spontaneous symmetry breaking. Now, the other consequence is when it fell, it could have fallen in any direction. What that means is there's a multiplicity of ground states, in fact, an infinite number, with the pen lying on the table in any direction. And that means there's a degree of freedom for moving the pen where it doesn't, you can move it as slowly as you can, and asymptotically, there's a zero energy mode in the system, which in particle physics translates into a massless particle. So a broken symmetry typically means a massless particle. In the standard model, it's even more complicated because the massless particle, we say it gets eaten by the vector particle. So the spin 1 particles in the theory become massive. But a massless spin 1 particle has no polarization along its direction of travel, can only be polarized transverse to its direction of travel. So it has two polarizations, two states, whereas a massive particle can have a polarization in its direction of travel, because you could have a massless particle at rest with the spin in this direction, and then you can move it in that direction, and its polarization is still in that direction. Whereas massless particle, you can't put to rest. So we need another degree of freedom to turn a massless particle into a massive particle. And in what's called the Higgs mechanism, it was actually invented by Anderson in condensed matter physics, and many other people contributed to the transition from the condensed matter physics idea to the particle physics idea, including Higgs. But it's called the Higgs because that's simple. If you've got 7 names, you've got to put one of them in. So that mechanism of turning a massless vector particle into a massive vector particle by getting rid of one of these massless degrees of freedom and combining it with 2 other degrees of freedom to make a massive vector particle, that's what's called the Higgs mechanism. And that's how you get masses for the W and Z. The bosons that mediate the strong interactions are very massive. So instead of having a point-like 4 fermion interaction, you have 2 fermions vector boson, two fermions. You spread apart the thing that was giving you the problem in the weak interaction by having this massive particle. And all of that, all those pieces existed, and Steve put them together in his theory of leptons, and that's how they work in the standard model. Again, I talk and I tell you what I'm put on my next transparency. So meanwhile, where was I in this story? Well, actually, I didn't have a job. I was a postdoc after my PhD in Germany at Daisy. And when I returned from Daisy, my husband, who's also at that time was a physicist, although he left the field shortly after, was offered an assistant professorship at Tufts. And I said, any place, any town where there's two jobs, Boston are likely to be one of them, because there's lots of universities in Boston, but nobody offered me a postdoc. So I decided, all right, maybe I'll be a high school physics teacher. And I took education courses and I did student teaching in a high school. And I actually loved the teaching, but I hated supervising study hall and telling the students they had to walk down the hallway and things like that. So I ran into another physicist, Joel Premack. Oh, I've got some things on here that I skipped. And so I'll go back to the offer letter if you want to hear about it. But at any rate, meeting Joel Premack, he was working at Harvard. He invited me to come and talk to them. And that's where I came back into the physics world of research physics. The offer letter from Daisy, I have to tell you that story. So my husband and I applied for postdocs, and we got a telegram from Daisy. It said, offers, letter, applications accepted, letter follows. The letter came by C-mail. And by the time we got that letter, we had to make decisions about all the other offers we had, and we turned them all down, foolish fools that we were. Because the letter came, it was addressed to my husband. It offered him a job. And then it said, as long as your wife works for us too, we will increase your combined family salary too. And the difference was less than half of what they offered him. So there was some kind of logic to that. At that time, they paid Americans more than they paid Germans because the exchange rate was so bad that Americans wouldn't have gone to that lab unless they had a higher salary. And they paid me the difference between one American salary and two German salaries. And the second year I was there, they paid me a full German salary. So I must have done something, but I didn't do much. It wasn't a good time in my career. And then, as I said, no job. But then I met Joel. So I did the education courses, met Joel Premack in Harvard Square, and decided to come talk to him. And I started doing a calculation with Joel Premack and Tom Applequist, who people here know very well. Tom and Joel and I did the first one-loop calculation, first higher order calculation in Steve Weinberg's theory of leptons. And we had a 't Hooft and Veltman's way of regulating the infinities, which had just come out. And that was what Joel was excited about, that told me I should come talk to them about. So we could do that calculation. And we told Steve Weinberg about it, and he was so excited, he invited us to his house for a sherry. So that was the beginning of my work on the standard model. And for the next semester, I had an office at Harvard. It was Shelley Glashow's office, because he'd gone to France to work with Mariani and Iliopoulos for the other piece of what's a very important part of the standard model, how it works in the quarks, making the quark sector work by adding the charm quark. You cannot make Weinberg's theory of leptons work for quarks without a fourth quark. Only weak interaction theorists took that fourth quark seriously because it fixed the big problem in the Weinberg model until experiment told us that quark exists. But that was interesting. So these two critical things had to happen. The ideas, Glashow, Iliopoulos, and Mariani telling we needed the fourth quark, and a 't Hooft and Veltman telling us we needed a method for regulating the infinities, And this was one that you could do that didn't destroy the gauge invariance and didn't destroy all the symmetries in the theory. So that was important. And I keep getting ahead of my transparencies. Obviously, I'm rushing. Oh, so I'm standing over here and I can't see what's behind me. But, this was really a big step forward to have the calculation. But Ben Lee and Bernard Zajustan took another big step forward around about the same time. They did a formal proof that the theory was finite to all orders, that the theory really worked about the same time as we did that first one loop calculation. And as I say here, they actually referred to our paper incorrectly because it hadn't yet been published. And they referred to it as Appelquist and Quinn. For some reason, they left Joel out. I think I'd been talking to Ben Lee, and maybe Tom had been talking to Ben Lee, but apparently Joel hadn't. So that's the way it went. But their papers were very, very technical. And also they were in a different gauge, if you know anything about, there were a different set of variables than the ones we were working with. And it took a while to make sure that both those two ways of looking at the theory were really identical. So elsewhere, another important and critical contribution is understanding how come we can have these quarks with fractional charges and never see them. This paper I'm talking about is the beginning of that description. What you have to understand are what are the interactions between quarks and how is it that quarks can't get out of being inside protons or neutrons or other hadrons. And this is a whole nother evolution, quite different from the weak interaction theory. And it's really a redefinition of the strong interactions. We keep talking about it without saying that, right? When you were in high school, you were probably told that the strong interaction is the interactions between protons and neutrons that hold them together to make the nucleus, right? How many people learned that? Put your hand up if that's what you learned. Did you know it's not true? Right? The strong interaction today is the interaction between quarks that hold the quarks together to make protons and neutrons. And protons and neutrons are neutral particles under that interaction. So what the heck holds them together to make protons, to make nuclei? The fact that in the nuclei, they're close enough together that they overlap, and the interactions between the quarks inside them has a residual effect, if you like. I mean, atoms are electrically neutral, but they make molecules, right? So it's the same story with quarks. Protons and neutrons are strong interaction neutral, but they make nuclei. And in fact, neutrons are only stable inside nuclei, which inside some nuclei, which is why there's only certain isotopes that exist, right? So the whole idea that there are these quarks made us rethink how we think about strong interactions. And it took a while for that to propagate into a way nuclear physicists think, but it's pretty much there now in terms of it. And then the fact that you need hadrons are not just three quarks. Protons are not just three quarks. They're interacting all the time. There's gluons between them. And those gluons can make quark-antiquark pairs. So hadrons are actually very complex dynamical systems. And quantum mechanically, they can, at any instant, have many quarks and antiquarks and many gluons, as well as those three quarks that gave us their quantum numbers. But that's all step by step. And why can't they get out? I mean, the simplest thing to talk about is, let's imagine an experiment where an electron and a positron collide and they disappear and they make a quark and an antiquark. And the quark and antiquark are flying apart. It's hard to wave my hands and hold a microphone. Okay, so imagine the quark and antiquark flying apart as fast as they can. Why don't we see a quark over here and an antiquark over there? Well, there's gluons between them because they interact. And Before they get the size of a proton apart, many quarks and antiquarks have been formed, and they fly out as groups of quarks and antiquarks. Maybe it's a pi meson and an anti-pi meson. Maybe it's 7 pi mesons and seven antiparticles of those pi mesons. All pi antiparticles of pi mesons are pi mesons, right? A pi plus antiparticle is a pi minus. Pi zero is its own antiparticle. So you just get pions. You can get protons and antiprotons. You could get whatever can be made energetically will come out. But the quarks, the strong fields will rearrange the multiple particles into hadrons before they get far enough apart for us to see them. So both in time scale and in space scale, quarks never get to the point where they can be individually observed. We have to look at them while they're inside the proton. And that's what my thesis advisor, BJ, told us how to do. Okay, so by 1974, John Iliopoulos gave a talk at a summer conference, which actually had the Standard Model in it, as we understand it today. So I can say the theory emerged over the period from 1967, when Steve Weinberg wrote his paper, to 1974, when all the pieces had been developed and put together. Of course, there was lots we still didn't understand, lots of work to do, lots of things to be tested. And that's what makes it exciting to have a new theory, right? We didn't have any experimental evidence for many of those pieces. And that, of course, was what we needed to say, this is it, this is the Standard Model. So in 1972, Kobayashi and Moskwa wrote a paper. This is technical detail. We knew from experiments since 1956 that a symmetry called CP, which really is the symmetry between particles and antiparticles, mirrored. It's a mirror symmetry between particles and antiparticles. We knew it was not exact in the weak interactions because of experimental results that couldn't have happened if that symmetry were exact. But in fact, 1956, we knew no way to write a theory that had that property. It seemed as if all field theories automatically had CP. They automatically have a bigger symmetry, CPT, where you particle to antiparticle, direction to opposite direction, and time to opposite direction, or in states to out states, right? The process of electron and positron goes to, say, pi plus and pi minus, goes at exactly the same rate as the pi plus and pi minus to electron and positron. That's CPT. That's a symmetry which all field theories have. We don't know any way to write a field theory that breaks that. But in 1956, we didn't know any way to write one that broke CP. And what Kobayashi and Moskwa said is that, well, if we look at this new emerging Standard Model theory, with 4 quarks, we can't break CP. It just isn't enough degrees of freedom in the freedom to do it, theory to do it. So we have to add another generation of quarks or something else. But they said, in fact, they gave several examples of things you could add to the theory that would allow you to break CP. And one of them was 3 generations of quarks. And in 1974, in the same experiment where charm was discovered, we found the first particle of that generation. Another lepton, the tau. So there's the electron, there's the mu, there's the tau. And it's a funny coincidence, which nobody can explain for you, right? When we first postulated, found the muon, we thought we were looking at pions. And we found a muon, and then we realized it didn't have hadronic properties. So we had to agree it was a lepton, not a hadron. And it's almost the same. The mu is almost the same mass as the pi. That's totally accidental. Doesn't have any fundamental reason. Well, it happened again. When we found charm, at almost the same energy, the electron-positron collisions could produce a charm quark and a charm antiquark. They could also produce a tau and an anti-tau. And that kind of messed up the interpretation of when we had this new narrow resonance that it was a charm anti-charm particle. Well, it should have decayed into a K plus and a K minus. So we should have had more Ks than pi's, more Ks compared to pi's above that threshold. And we didn't. And so people were trying to find all kinds of other explanations for this new particle, not charm. But it was actually because the tau was also decaying to hadrons. And the two thresholds being very close to one another had people confused for a little while. But once we had a tau, there's a work by Glashow and Georgi telling us that unless you have the same, a match between the number of lepton pairs and the number of quark pairs in your theory, there's certain technical problems with the theory. So once we had the tau, we could postulate that, in fact, there had to be 3 generations of quarks, and we could have the CP violation explained by the 3 generation of quarks. But it took quite a while to get to finding, particularly the fourth, the fifth and sixth quarks. The fifth one is bottom. That took a while. Top is so heavy, it took much longer to find it. You needed bigger accelerators, et cetera. So now I've mentioned this asymptotic freedom. I told you when we did current algebra, we assumed that the quarks behaved as if they were free at high energy. It turns out the new theory of strong interactions, QCD, the gauge theory, the non-abelian gauge theory, has that property. And that was another Nobel Prize. It was done by Politzer at Harvard and Gross and Wilczek at Princeton. Wilczek was a graduate student. Gross was his advisor at Harvard. It was Politzer, and Sidney Coleman was his thesis advisor, but didn't put his name on the paper. So there were 2 graduate students who were given the problem of, does this theory have this property? And they both did it, and they both got Nobel Prizes for it. So actually, David told me and Tom about his result when his advisor, Sidney Coleman, was down at Princeton talking to the other guys. And we asked a stupid question. We said, but is it gauge invariant? For the people who understand that word, nowadays it's clear that it is gauge invariant, but wasn't clear to me at the beginning. And we sent him away to answer it, and it wasn't clear to David until he went back and thought about what he'd done. So that probably slowed him down a little in publishing the results. And the 2 results were published at the same time. So sometimes you need to know the answer to stupid questions. And anyway, the right way to think about it is there are no stupid questions. This is a Sidney Coleman quote. There are no stupid questions, only stupid people asking them. So I was the stupid person. It's really only ignorant people asking them, and ignorance you can fix, stupidity you can't. Okay, and it's good to ask ignorant questions because you learn. But anyway, the theory has really come together, and at Harvard by the end of '73, I think we were really talking about it. We went below, this is just for fun, I mean, how people work together. Georgi and Weinberg were by this time Glashow and Weinberg were in the same department, but they never worked together. But the group worked as a group of the whole. So the younger people like me and Tom and various other people in the department could work with either or both of them, but not together serially. So we would, all of us, interact together. And I think Howard was the person that Shelley used. Shelley would come in with 3 ideas every morning. And Howard would shoot down most of those ideas with some piece of data that told you it was wrong very quickly. So sometimes that's the pairing that makes ideas work, and only the good ones get published. This is a story just for the fun of the story. This is not a paper you should look for. But first of all, obviously we were having fun because we wrote this paper as a play, right? And the play had 4 characters. It had a naive quark theorist who thought of quarks like Gell-Mann, and a sophisticated theorist who thought of quarks like the way we understood things at that time. It had an experimentalist, and it had a computer, somebody who did the calculations. And the paper was written as an argument between these 4 people. And we actually put it on as a play, as a Harvard colloquium at that time. So clearly we were just having fun. But writing that paper was another story. Let's see if I say this. A word about atmosphere. So while we were writing that paper, after lunch in Howard's office, Howard smoked a pipe. Alvaro and de Ruhula and Shelley Glashow smoked cigars. And I was pregnant with my 2nd child. So I opened the window and I sat on the window ledge to be part of the discussion. And when they started to complain it was cold, because it was getting into the fall, it was getting cold, I just had to close the window and leave the room. But we were having fun anyway. So the atmosphere was very inclusive. These people were not putting me aside, and they didn't object to the fact that when my babies were born, each of them spent 6 months in the Harvard physics department. And I was lucky. I had babies who generally kept quiet. The only time I had to walk out of a seminar, my friends accused me of pinching my son. But that wasn't true. It was just he wasn't comfortable that afternoon for some reason. So this I've said most of, but I will go over it again, because the day of discovery of charm in the experiment was probably the most exciting day in the life of any particle physicist who was alive at that time, because we had all the pieces theoretically, and we didn't have this one piece experimentally. And the experiment, particularly the one, there were 2 experiments that both published the same result at the same day, but the one at SLAC was just completely obvious. They can say, we discovered charm. We started on November the 8th, 1974, and on November 11th, 1974, we discovered it. So they were going back and looking to refine a feature in their data, and it took them a weekend. And they'd actually been arguing with Bert Richter, who was the lead person on that experiment, for the time to do that. And eventually they convinced him. He said, oh, you can waste the weekend. But when they saw the results on Sunday evening, which was November the 11th, 1974, we particle physicists call that the November Revolution. It was the beginning of the establishment of the Standard Model. And it was tremendously, dramatically clear that they'd seen something new. And for those of us who were thinking of charm, very exciting, because we were now seeing what we needed to see in order to say we understand the weak interactions of hadrons. So my way of talking about this, yes. So that was November. In October, Tom and I and David Politzer were talking about Tom and David's paper on charmonium, which is a particle with a quark and an antiquark. That's the big discovery. So this is before the discovery, but after Tom and David have written a paper predicting that discovery. And Shirley walked by with Howard Georgi and Alvaro de Ruhula, and he listened to us for a while. He said, do you mean to say I'm in a room full of people, 6 of us, who all believe in charm? Well, 2 months later, he could have found a much bigger room. And so I think there are a few times when a discovery is that you can just put a line and say before and after, because experiments take time. And generally it's a slower process, but that was a very dramatic move. Now, the other piece I've talked about this really, but I didn't talk about who started this. The idea that quarks are confined, the idea that they can't get out, the story I told you about hadronization, the process by which quarks, the strong interactions make additional quarks. I think it really started with Ken Wilson's work on explaining how the strong interactions work. I mean, the whole idea that you look at things at different scales, and people doing lattice calculations, which is a way of calculating the strong interactions, putting by approximating space-time by a lattice of points. Actually, you approximate the theory by allowing the quarks to be at the points and the gluons to be at the links. You can put the whole theory into a way that reduces it to something you can calculate on a computer. It takes big computers, and there's a lot of work gone into making this method work better and better with bigger and bigger computers and better algorithms for computing. This is the way we understand a lot of what we understand now about strong interactions and how the spectrum of hadrons that we see comes from the set of quarks that we have. But the fact is, it's really a strange notion, right? A proton is made of quarks, but most of its mass is not the mass of the quarks. Now, until we got to this kind of a theory, if you had something and you took it apart into its pieces, most of the mass of the thing came from the mass of the pieces, and the interactions just made small corrections to that, right? You take an atom, most of the mass of the atom is the sum of the masses of the protons and neutrons in its nucleus, and the electron masses are tiny compared to that, and the binding energies, the differences in mass of the nucleus from the mass of the free protons and neutrons, which is negative because they're bound, is small compared to the mass. But when we get to the proton, most of the mass of the proton is coming from the interactions and coming from the fact that the quarks, by those interactions, are confined to a very small space. So they have to have a very small wavelength as their maximum wavelength of the waves that are adding up to make that state. And that means, because wavelength is inversely proportional to energy, most of the energy is the energy of that. It's the kinetic energy of the quarks, not their masses, that is giving you most of the so it's a very different composite than we'd ever seen before. And again, that took time to understand. How can you have a particle whose mass is not the mass of some of the masses of its constituents? Right? That took a while. So there's two things that are very peculiar in this theory compared to any prior theory. And when something's different, it takes a while for people to understand it. And so there's interesting work to be doing when you have a puzzle like that. Saying, well, it can't be, isn't the good answer. Figuring out how it can be is a very interesting set of challenging puzzles. I am supposed to end at 4:30, right? What? No, I'll end it. I'll try to end. Okay. I just want to talk a little bit about that. So I was at Harvard. My salary was half paid for my research work and half paid for teaching. When I was about to have my son, or actually when my husband and I decided we'd have a second child, was when the physics department was assigning teaching requirements for the next year. And I said, I better get myself a course that I can get out of if I'm going to have a baby. So, but I didn't know because I wasn't yet pregnant. Right? So I quietly told the department chair, we're planning to have a second child, and you probably should give me a teaching assignment for second semester next year that you can find a replacement for me easily if the child arrives. Well, within a week, everybody in the physics department knew that and if I wore a loose dress, people would say, are you? It was really strange. But at any rate, my son was born in January 74. Harvard messed us up a little bit because they changed the final exam. So he was actually, they changed the dates because they were trying to save energy by not closing down the building and heating it up again. And so the final exam for the course I taught in the fall semester was actually after my son was born. And I was grading finals by the time when he was 3 days old. But it was supposed to be happening a little earlier. And then I kept him in the physics department. It was also that day, the day he was born, I got a letter from the Sloan Foundation telling me I had a fellowship, which is a very nice fellowship to get. But in order to get it, you have to submit a budget within 3 days. And I knew I was on the way to the hospital. So I was working in the physics department. I took the letter up to the chair of the department and said, "Can you do something about this? I'm going to the hospital." I'm telling you this story because I think it didn't happen in many physics departments. The people, he wrote a letter to the Sloan Foundation and they allowed me to submit my budget later. But he had great fun writing that letter. He wrote it, "Your letter arrived in such and such a day, and James Quinn weighing so much arrived on such and such a day." So, and I took that leave. Then since I got the Sloan Fellowship, that was very nice because I could follow my husband to his next job, where he was changing fields and going into a new field, and he had a job at SRI near Stanford. And I said, well, I'll just go to Stanford Physics Department for the next year with my Sloan Fellowship for the next semester. And then we'll decide what to do next. So I went to Stanford, and that's when I worked with Roberto Pache for the work which people know my name is associated with. So I'm just going to show you a couple of pictures. These are my kids in 75. This is me. This is actually in a brochure on women in physics from 1976, this photo. So that's how I still have it in my polyester suit in the physics department office. But am I going backwards? No. So we have, I'm just talking about what I did in that period, other than Pache-Quinn symmetry, which was 76. I wrote a couple of papers with Steve Weinberg. One of them says that when you put together the standard model strong, weak, and electromagnetic interactions and watch how they evolve with energy at a very high scale, since the strength of the electromagnetic interaction goes up and the strength of the strong interaction and actually the weak interaction too come down, they eventually all meet at a very high scale. And this was, this I think is now in all the textbooks, so it doesn't get referred to very much. But I think it's actually one of those key papers that make understanding of a theory better. It's part of how you fix the problems of QED, but it bumps into those weak interactions as it goes up. Its coupling constant goes up because that coupling constant goes up is part of the problem of the high energy theory. For QED alone is not a good theory. It's only a good theory when it's combined with the weak interactions in this way and the strong interactions eventually. And the paper with Poggio and Weinberg is about how you produce quarks, but you see hadrons. And how do you take the quark predictions and make predictions for the hadrons? And if you average over energies, then this process of hadronization gets smeared out, and you don't have to look at it at the first order. You can count the hadrons if you like, or look at the hadrons and learn something about the quarks. And so that leads to thinking about jets and an idea which is now called quark hadron duality, that calculations with quarks can tell you something about what hadrons do, even though you never see the quarks. I told you this. Consolidation. Everything since then. By 1976, I've told you about the tau meson. The D mesons were important. That's where you get to see, instead of charm and anti-charm in the same particle, you see a charm particle and a like quark, a U or an S or a D. And in a meson, a D meson is a charm particle in either a D or an S antiquark or vice versa. And that discovering those in 1976 was really, okay, now we've got all the pieces we needed to say this standard model is right. This is what we're seeing. We're charm. Those particles we thought were charm really are charm. And so that was another important development to get to the point where the Nobel Prize for the standard model was given. Now, since then, we've been consolidating. And I just want to show you a couple of pictures because it's absolutely fantastic that we have a theory, and every line in this graph is a different experiment that measures the same parameter in the standard model. So we've got all those measurements, and any one of them could say this model isn't working, but they all agree. This is what I say when there's lots of data. The theory is good. You don't need to know what all those different experiments are. Having that many different experiments, measuring the same parameter at different energies or in completely different channels in a decay process or whatever. This is just one example of the many places the standard model works. This is the CP violation. So CP violation, there's really one CP violating parameter in the standard model, and it's the area of that little triangle in the middle of these pictures. And what we have to do is the base of the triangle is normalized to 1. So we have to measure the length of the other sides or the angles, and different experiments measure the lengths of the angles. And each different color is a different experiment that's measuring where is that vertex of the triangle. So the first graph, 1995, that's what it looked like. And then experiment works very hard. And by 2015, we have all these 7 or 8 different measurements here, and they're all measuring that parameter, and they all agree, which says, actually, we hoped they wouldn't. We thought this might be a place where we could see something where the standard model doesn't quite work, and it'll tell us what we need to add. But there it is. The standard model tells us that the CP violation in the hadron physics comes from having 3 types of quarks and having the combinations of quarks that pair with, of down quarks that pair with heavy quarks, up quarks, down type to up quark, be well determined in those 3 generations. So we need 3 generations, and we need that the quarks that have good properties under the weak interactions are linear combinations of the quarks that have definite masses for the down type quarks. And that's what gives us this triangle. We can measure it. And again, the theory is incredibly good. The amount of experimental work, right, that goes into this, and we're starting quite a while after the theory is written down, but the amount of experimental work it takes to test the theory and say it is a well-tested theory is an incredible amount of work. This picture is hundreds of people working for multiple years, and it's, to me, quite amazing. I got interested in high school physics. I always was, I told you I was a student teacher. I was thinking, and I ran programs for teachers at SLAC in the summer, like undergraduate research experiences and teacher research experiences. It's good for teachers to have that experience too. And some of the teachers got me involved in developing that. That's a picture of me on the floor of my house with a big piece of paper with colors on it. And this is a picture of a chart, which you've possibly seen on the wall of a classroom somewhere, that describes the standard model in a simplified way and has a little bit of detail about it. I did this working, the first version of this poster came out, I think, a little after this picture. This picture was taken in 1988. And the colors, actually, the crayons that my son grabbed and he was coloring in the poster for me. So that's just to say there's things you can do outside. Now, actually, I lie when I say the standard model covered all tests. The standard model had only one It had no masses for the neutrinos. And it didn't need to, because in the weak interactions, only left-handed quarks are involved. So we could leave out right-handed quarks and left-handed antiquarks. We had left-handed quarks and right-handed antiquarks, but not the other. And finding that the neutrinos had mass, that's another whole long story. But the experiments have shown us that neutrinos do have masses. And again, the states which have definite weak interactions are mixtures of the states that have definite masses. And that's what neutrino mixing is about. But this introduces other possible CP violations into the theory. But unfortunately, we don't yet know enough, and we may never, because they may be at high enough energy scales that we really can't test them. But this is another option for where there's CP violation. Because having done all this, we've discovered that the difference between matter and antimatter in the standard model quark sector is not enough to explain the difference between matter and antimatter in the universe. Early in the universe, there were equal amounts of matter and antimatter. Now they're unequal. We see lots of matter objects and no antimatter objects out there. There are some antiquarks and antileptons, but very few compared to the matter in stars, etc. So this tells us there's something else beyond the standard model. Maybe it's in the neutrinos. Maybe the neutrinos do it. Maybe it's something else. We don't know how the imbalance between matter and antimatter in the universe got established, but it wasn't through the quark CP violation. All right, that's, I think, enough. I didn't quite finish on time, sorry, but I'm open for questions.
So the way we're going to handle questions is we'll start with the in-person questions, and then we'll do the ones on Zoom. If you're on Zoom, feel free to leave a question in the chat, and we'll get to those at the end. For those in person, just feel free to raise your hand. I'll come over to you with the mic, and just introduce yourself before you ask the question.
You need to hand them the microphone too.
Yeah. Mm-hmm.
So the Zoom people can hear your question.
Hi, my name is Elise. I'm a postdoc. So I guess for those of us who are in the field of particle physics, these days we hear a lot of people say that the field is kind of struggling because we haven't made a big discovery in a long time. And so I'm curious to hear what your perspective is, having seen the whole history. Do you feel like we're at a stalling point, or?
Well, there's two ways of looking at it. One, you can say we're at a stalling point, and the other you can say, well, it's wide open for new ideas, right? Unfortunately, the theory's too successful, right? That means there's not a lot of evidence for which way to go in the new ideas. I think, as I was telling you, when I entered the field in the 60s, it was the other way around. We had a huge amount of data and no explanations. That's a much easier place, at least for a theorist, to make progress. It's equally hard for an experimentalist as it is today, because there's no direction to go to say, what piece of data do I need to fix this situation that we can't explain everything? So I think no matter what era you're in, there are things which are difficult. And it gets more difficult. The more we know, the harder it is to figure out what it is we don't know. And anyway, when you're doing research, the hardest thing about research is asking the right question, right? You have to ask a question that will have an interesting answer, that the answer will be interesting to people. But you also have to ask a question where there's something you know and something you can do to move forward on that answer. You don't just want to ask a question where you have no idea where to go, right? So how do you figure in this current situation where the theory is very successful, it's hard to know what are the good questions. Doesn't mean there are none.
I'm wondering if you care to tell us how the idea of the axion came to be.
Well, yes, a little bit. Did I even have, no, I didn't have a slide here. All right, so we were trying to solve a completely different problem. The problem is, I said the standard model has CP violation, but the strong interactions don't, or at least the CP violation in the strong interactions is very small. And we know this experimentally. The electric dipole moment of the neutron is in any natural units very, very small, like 10 to the minus 12. And that tells us that the CP violating parameter, which in the standard model you can put into the strong interactions, it's, for those of us those of you who know the formalism, it's theta FF dual, where the F is like the F of electromagnetism, a function of derivatives of the gauge fields and gauge fields, but it vanishes in QED, it doesn't vanish in QCD. That's a term which is CP violating, and there's no reason not to have it in the strong interaction theory. And if you have CP violation in the weak interactions, they can induce that term in the strong interaction theory. So the puzzle was, why is that term so small? It has to be 10 to the minus 10. Theta, which is a parameter that can go from 0 to 2 pi, is less than 10 to the minus 10. So that was the question. How we got to the answer is a whole nother story, but the answer involves something which is called Pache-Quinn symmetry. That's a symmetry like the symmetry of that pencil. It's a circular symmetry in the mathematics, and it has a zero mode, which is broken when QCD, it's broken by the QCD vacuum value of the quark fields. And that tilts it a little bit. So instead of being a zero mass particle, it's a low mass particle. Now, the fact is that Roberto and I did not notice this. We looked at the very simplest version. So to make this symmetry work, you have to add more than one Higgs doublet to the standard model. So you have to add at least one more Higgs doublet. You can add as many as you want, but the simplest version is to add one doublet. And that's the only theory we looked at. And that had a light particle. And that light particle coupled strongly enough to ordinary matter that we knew that theory would be quickly ruled out. So we talked about it, but we kind of buried it in the paper. Like Steve Weinberg, we didn't want to deal with the complications of what model would survive all the tests. We just wanted to put out our idea. So we didn't think about any of the other models. Steve Weinberg actually called me up. He said, do you realize that your theory has a pseudo-Goldstone boson? And moments thought, I said, Steve, obviously you're right, but no, we didn't notice. And he said, well, in that case, I'll publish it myself. In other words, he was inviting me to join him in the paper if I already knew. It's a nice guy, Steve Weinberg, right? But so the axion got its name because Frank Wilczek also noticed that, and he wrote a paper and he called it the axion. When we were playing with the light particle in our theory, we called it the Higlet. Other questions?
Thank you for the wonderful story. I'm Reina Mariama. I do axion searches. I was struck by how collaborative your work environment was, and you said that it was a very welcoming. What would it take, for us to get to the question, to inject this kind of thing in the particle physics world now? I do think there are many questions that are intriguing now, like the neutrino example that you brought up, dark matter.
Well, I think I was talking about theoretical collaboration. Experimental collaboration in particle physics these days is mostly very large scale, although that's not so true for things like axion searches. There are smaller scale experiments, and it's where they're not high energy. It's really not high energy physics, right? It's particle physics. And there are non-high energy experiments, which are smaller scale, which are very interesting. And I think there's a lot going on in that domain today, because I'm not the first person to notice this. But what does it take to have a collaborative group? Well, it's partly a matter of personalities. It's partly a matter of developing, and this is a question: climate in a department, climate in a community, climate in a group. The leadership of the group has some responsibility for that, and can make it be a climate where young people can thrive, or a climate where they feel excluded. And I don't know how it worked. I think it was partly the physics was driving the climate, because the physics was just bubbling. It was easy for everybody to, there were plenty of problems to go around. So, but I also think it's personalities and leadership that can make it work or make it not work, right? Make people feel that they have to fight to be included. And there was some of that. You know, you had to establish yourself as being smart enough to be one of the boys. But after you got to the point where you were part of the group, then it was very open.
Thank you.
Hi, I'm Aria. I'm an undergrad here. Thank you for coming to talk with us. I was wondering, how did you get interested in physics and particle physics in particular?
Well, I have to go back a little history. When I entered Melbourne University, I knew I wanted to do some kind of science. I didn't really know what. And I was offered a cadetship. A cadetship is something that it's like a scholarship. It pays your tuition. It also pays you a salary while you're a student. But in return, you sign an agreement that you will work for the organization that's giving you the cadetship for 5 years after you finish your degree. And I was offered this by the Weather Bureau. And there's a penalty if you leave earlier, right? You have to give back some of the money or all the money. So my father said, look, it's cheaper for me to pay off the bond if you decide to leave it than to support you for all these years. So why don't you take this? So I took it, and I would have been a meteorologist, except my family decided to move to the United States. And so I left. So I arrived at Stanford. Stanford gave me a year of credit for my last year in high school and 2 years of credit for my 2 years at Melbourne University. So I arrived with enough credit to become a senior and no major. Right? So I had to find a major that would fit with what I'd done, that would let me complete my degree as soon as possible. And actually it took me a year and 1 quarter. And since I arrived mid-year, that wasn't a problem. And I took my notes from my classes at Melbourne University, and I went to various departments that I thought might work. And in physics, I was sent to an assistant professor named Jerry Pine, who was very flexible. He said, look, let's not worry about what the requirements for the major are in terms of courses you must take. I don't know what you know. If you think you've covered a course, I'll tell you should get credit for it. And I kind of liked that way of doing things. So I went to Stanford, not Berkeley, where they were much more rigid about what credit they'd give me. And I was a physics major at Stanford because I was a person in the physics department who was being flexible. Right? And that's really why I became a physics major. Now, at that time, SLAC was being built. So there were people in the physics department who were very excited about this big new instrument that they were going to have. And so I guess I got interested in it, and faculty encouraged me to go on to graduate school, which I would not have thought of unless they found an Australian postdoc and sent him to tell me that I should go to graduate school. So I don't think I would have done it without that prompt. So somebody took the trouble to tell me that I should do that. And graduate schools, another funny story. So my undergraduate advisor was talking to me about applying to graduate school. He says, you know, graduate schools are reluctant to accept women because they get married and one thing or another, and they don't finish. But I don't think we need worry about that for you. I literally sat there thinking, did he hear what he just said? But it was true. I stayed at Stanford Graduate School because no other school offered me graduate study, right? I wrote to Princeton and they said, we do not normally accept women. I was asking them because I wasn't sure. And so it was a time where it was not common for women to go to graduate school in physics, but I had already established myself at some level at Stanford. And so I stayed at Stanford, and particle physics was big. And that's why I became a particle physicist. There was something exciting going on, and I got excited.
Hi, Kenny Fan, undergrad. I was curious whether you believe our understanding of particle physics could inform whether or not our universe was a simulation.
I don't even know what that means. First of all, the universe was, it is. and the idea that it is not, I mean, there are, I think I'm very pragmatic. The world around us is something, the word real means something that to me is just, what can I observe? And of course, we can observe a lot more when we have very sophisticated instruments, but all that particle physics can do is tell us more about what we can observe and tell us how to interpret what we can observe. And to me, we can call all of that real, but whether you think that reality is somebody else's simulation, that's pure speculation. We can't even answer the question, which I think is a much more real one. Do we live in a multiverse? Because the other parts of the multiverse are something we can't observe. There are implications which we can make from mathematical theories of physics. So it's plausible that they're there, but it's not a question we can answer in a scientific experiment. So, because they're causally separated from our part of the universe. But that's much more close to physics than the question of whether the universe of the multiverse or whatever it is we live in is a simulation.
So if we have no one else in person, I wasn't keeping an eye on the chat. Were there any questions on Zoom? Let's see.
You need to look at the chat.
Yeah. Well, okay. I don't think we have anything. Last minute call. Going once, going twice. All right. Well, in that case, can we please give one more big round of applause for Professor Quinn?
Thank you very much.